Mechanical energy in non-conservative systems. So far, we have seen systems in which any gain in kinetic energy must be accompanied by an equal loss in potential energy. These systems are conservative systems because the mechanical energy is conserved. We now will see systems in which mechanical energy is not conserved. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. Let us list the key elements to discuss non-conservative systems. A system consists of two or more objects. For example, a body in free fall. In this case, the system is the body, the earth, and the air surrounding. Another example, a body colliding with a spring. When the spring has released, the block moves. By system, we mean the body, the spring, and the surface. We will proceed by introducing new terminology. For any system, internal forces are the forces that the particles of a system exert on others. For example, the weight of a body is the result of the interaction between the body and the earth. A spring pushing a body is another example of internal force. External forces are the forces exerted on any part of a system by a body outside the system. For example, kinetic friction and air drag. If there are no external forces in a system, we say that it is an isolated system from its environment. No work is done on the system from outside. Therefore, energy transfers may only be going on within an isolated system, between, say, kinetic energy and a potential energy, or vice versa. But it cannot be increased or decreased. For that case, the mechanical energy is conserved. An isolated system must also be frictionless. In plain English, isolated system, a system in which only internal forces are doing work. If there are forces applied from outside a system, that is, external forces, we say that it is a non-isolated system. Work is done on the system from outside and energy can be transferred between a non-isolated system and its environment. For that case, the mechanical energy is not conserved. In plain English, non-isolated system, a system in which internal and external forces are doing work. The external forces are called non-conservative forces. The work done on the system by all non-conservative forces is equal to the change in mechanical energy of that system. Now you can see where non-conservative forces got their name. The diagram shows the vertical cross-section of a surface. A and B are 2 points on the cross-section, and A is 5 meters higher than B. A particle of mass 0.35 kilograms passes through A with a speed 7 meters per second, moving on the surface towards B. Assuming that there is no resistance to motion, find the speed with which the particle reaches B. Assuming instead that there is a resistance to motion and that the particle reaches B with speed 11 meters per second, find the work done against this resistance as the particle moves from A to B. In the first part of the question, there is no friction in the system, so this is an isolated system. The mechanical energy at state A is the same as the mechanical energy at state B. We know that the loss of gravitational potential energy as the particle goes down the slope is equal to the gain in kinetic energy over the length of the slope. In the second part of the question, we must consider that there is friction between the particle and the environment. So this is a non-isolated system. The mechanical energy at state A is not the same as the mechanical energy at state B. The mechanical energy at state B is equal to the mechanical energy at state A minus the amount stolen away by friction. In other words, the change in the total mechanical energy of the system is equal to the energy dissipated by friction. We write the work done by non-conservative forces is equal to the change in the total mechanical energy. The calculated value of the work done by non-conservative forces is always negative. Friction always reduces the mechanical energy of a system. There will be a transfer of heat. The friction acts to slow the motion because the macroscopic ordered kinetic energy of the moving molecules is transferred to the random disordered kinetic energy of the molecules of both surfaces. There will be a rise in internal energy and temperature. Thermal energy will also be transferred to the surroundings. A block of mass 3.5 kilograms is launched from a spring of constant 300 newtons per meter that initially compressed a distance of 0.4 meters from its equilibrium position. After leaving the spring, the block slides on a horizontal surface with frictional coefficient μ. Suppose that the part of the horizontal track is rough with a length of 0.5 meters. Find the force of kinetic friction if the block reaches a maximum height of 0.10 meters. The presence of friction means that mechanical energy is not conserved, but we can still identify the kinetic and potential energy in the initial state. The kinetic energy is zero and the potential energy is that of the spring. In the final state, there's gravitational potential energy. The non-conservative frictional force converts some of the block's mechanical energy into heat. The block comes to rest when it reaches a maximum height of 0.10 meters. The work done by kinetic friction is equal to the change in the total mechanical energy of the system. The calculated value of the work done by kinetic friction is always negative and equal to force times displacement times cosine of 180 degrees, because the kinetic friction acts in the opposite direction to the motion. An 850 kilograms roller coaster is released from rest at point A of the track shown in the figure. Assume there is no friction or air resistance between points A and C. What average force is required to bring the roller coaster to a stop at point D if the brakes are applied at point C? No energy is lost from the system between points A and C. The amount of energy in the system remains constant throughout. This means energy can be compared at any 2 points. But we are asked to find the force required to stop the roller coaster between points C and D. So there is friction, and the work done by non-conservative force is equal to the change in the mechanical energy between points C and D. At point A, the kinetic energy is zero. There is only gravitational potential energy. At point D, the kinetic energy is also zero, but there is still potential gravitational energy. The work done by kinetic friction is always negative and equal to force times displacement times cosine of 180 degrees.